Okey-dokey. Sure. Hello, everybody. This is Professor Ma, and this is the sections on Maclaurin expansions. Um, we started with polynomials. We say polynomials and the square root stuff like that. They're called algebraic. In particular, in the case of polynomial, what we mean by algebraic means we can perform arithmetic operations on it, and I will get the answer if I plug in the numbers. Okay, so uh, arithmetic operations as a check mark by default, but not for functions like sine of x or log of x. In other words, if I give you a number x equal to 2, it may ask you to compute log of 2. There's no way to take the number 2 and dice it and somehow, well, later on, well, there is a way. But from the, from the outset, that they seems like it's impossible. Okay. So, and these type of functions, we call these transcendental, okay, versus algebraic. Uh, Transcendental in dictionary means non-physical, okay? So means like you have this religious connotation of transcendental. What it means is it means more closely non-physical in the sense the computation is not finite. It's infinite decimals. Like it's not something like I know exact like polynomials. Okay, so in that sense, there's a break between finite and infinity. So that's what the word transcendental means in terms of their computations. This type of formula log of x and sine of x. And what we're going to do is try to bridge these two. Okay, so how can we expand the polynomial somehow becomes can compute log and sine, and this is exactly what we're going to do. What we're going to do was using these infinite expansions and power series. Okay, so so here we go. Okay, so we start out with observations. First of all, how to approximate a polynomials with the lower degree terms. Suppose I have a polynomial here is degree n, and how can I use lower degree formulas to approximate these? Here, for example, here's a polynomials and with the roots minus 1, 0, 1, and 2. So it's easy to graph. But if I were to expand it, then I get this polynomial, which I line up from smaller degree to larger degree. Okay. And let's take a look at the graph. Here's a polynomial against the first term. Okay. Meaning linear functions. Y equal to 2x is the best linear function. So in that phrase, is the lower degree are the best approximation. It means the same degree linear terms, 2x is approximate this formula the closest. Okay, and then if I take the first 2 degree, and so that now I'm getting a parabola, then this will be the best parabola that approximate at that point 0. Okay. And then this, of course, is a cubic. And if I use a cubic, this is the best third degree approximations at the point 0. Okay, so we're doing this at the point 0. Let me emphasize. So only concentrate at that point around that neighborhood. Of course, if I use all fourth degree, I get the entire graph. We cover exactly P of x. Okay, but on the other hand, notice I can recover the terms if I don't know these expansions, okay, or in general, I just replace this P of x by f of x, okay, and I can recover these terms by taking derivatives, okay. Oh, by the way, and why is this approximation gets better and better a higher degree is because we're doing this around 0. So the higher and higher degree becomes less and less important. So the graph approach better and better to the entire polynomial, okay, its shape. Okay, so given a formula polynomial, here is a method of recovering the polynomial, okay, So let's start with actually an infinite differentiable function around x equals 0. Okay, we're going to define the following series of polynomials, and so we call this the nth degree polynomials or nth degree Maclaurin polynomials. It will surely is okay. So this is the formula for the nth degree Maclaurin polynomials. Okay. And of course, this means take derivative twice, take derivative 3 times, take derivative 4 times, n times, etc., etc. If you first look at this formula, says what is this about? Well, let me give you a demonstration. Let me specifically, for instance, let me take a polynomial p is equal to x plus 4 times x cubed. Okay. And suppose I want to recover, here's a demonstration how I can recover this coefficient A4 in front of x cubed. Okay, the things we are going to use, the knowledge we're going to use is that the following things. Given a polynomial of third degree, if I take the derivative 3 times, I'm going to left with a number. Okay, this is true for fourth degree. If I take it 4 times, so if I take the same number of derivatives as the degree, I wind up with a number in front of the, well, you'll see. So let me take the first derivative. I'm going to do it 3 times. Okay, and the x becomes 1. This becomes 3, 4 times 3, x squared. Okay, second derivative is going to be 0 plus 4 times 3 times 2 to the x to the first. Then third derivative, now it's a number, plus 4 times 3 times 2 times 1, which is called what? 24. Okay. And notice, how do I get from this answer, 24, back to the number 4? Well, the number of times you take derivative is 3 times, so therefore the contribution from the multiplication is n times n minus 1 times n minus 2. This is 3 times 2 times 1. In general, it's n factorial, and in this case 3 factorial. Okay. So in other words, I take this number, take the derivative 3 times. Okay, I divide by the 3 factorial, and this will give me the number 4 back. That's basically what this formula says. How do you recover the number in front of the degree? Okay, you just have to take the derivative and then plug in the numbers and divide by the number of power multiplied downwards. And this is the general form of the Maclaurin polynomial, degree n. In this formula, we'll only do up to degree n. If we were to do up to infinite many times, I get a power series. And this is the Maclaurin series. It's a power series. Okay, and these we call Maclaurin expansions. One more time, what do you mean by Mach? The Mach refers to we are doing this at x equal to 0. Okay. Later on, if we change the focus to another location than x equal to a, then we call that Taylor expansions. Well, anyway, first thing to notice, if I were to start out with a function infinite differentiable, I make up this polynomial p of n of x, and what's the relationship between these two things, a polynomial and a function itself? Well, it turns out their values are from the zeros, which means plugging the number, up to the nth derivatives, plugging the number. They were the same. Okay. So if I take derivatives and first derivatives, okay, will be equal to the first derivative at 0 when I plug in. Why? Because the first derivative has a bunch of x's behind it. I'm going to plug in 0, then I'm just going to get the number out. It just it just a particular computation that will pick out the particular terms, and then all the other terms become zero. So with that formula. Okay, so therefore all the derivatives are the same. Since it's an nth degree polynomial, so it stops here. Okay, it agrees up to the nth derivatives of the functions. Okay. And in particular, okay, here's example A. Basically says if I started out with this formula that actually itself is a polynomial, and apply that procedure, take derivative divided by factorial, plug in that, multiply by x to the power. You go to the computations, you find out, you just confirm what we exactly expected, that is, we're going to get the formula f of x, the polynomial back itself. Okay, so just that you're going to get each coefficient in front of the formula. Okay, so you can read this. Basically, just a round of loops of calculations, and then it concludes with a following statements. Okay, that is, if I were to calculate the Maclaurin polynomials of a polynomials, I recover the polynomials. Okay, where I cover each segment of the polynomials until I get to the entire polynomials, then my plus zero beyond that. Okay. Of course, the more interesting things is that these Mach polynomials, if you think about it, and if I have two different functions, f and g, and if I add them, then their max polynomials add. If I multiply f times g, okay, their polynomial multiply. Okay, since each one expansion is of functions, and so we can calculate the polynomial of max expansions using the method sort of approach of with those things we do with derivatives. That is, we calculate the Mach polynomials for each family, and then we can get the family from each basic formulas, and then from those basic expansions, I can calculate other more complicated expansions. I can make it possible. Okay, actually done by hand, it's lengthy, right? But still, it's possible. So here is the Mach expansion of e to the x. I wouldn't bore you with it. You can go to the calculations. You find out this is the Mach series of e to the x. Okay. And this bottom is the power series associated with the e to the x. Okay. And how about the trig functions? Oh, let's take a look at the approximation using this Mach polynomial. So here's e to the x. Okay, and here are the linear approximations. And here's the best polynomial, the green line at 0. And then the next one is a cubic, and the purple line is the best cubic. Okay, approximation. And if I were to blow up in the center and look at the point, and you will find out that the purple line, keep blowing up, you will get to a point where the purple line is closer than everybody else to the black line. Okay, so it does work as approximations. Okay. And here's a Mach expansion of sine of x, and where's the algebra? What's the algebra? We need to keep track. The algebra we need to keep track is when you take a derivative of a sine, because we're going to take derivative many times. It goes in cycle. Okay, so here's a cycle of derivative, and I'm going to plug in a 0. So Mach expansion is at 0. So if I were to plug it in, then what I find out is that I will get number 0, 1, 0, minus 1, 0, 0, 0. It goes in this cycle, 0, 1, 0, minus 1, 0, 1, minus 1. Okay, all the even derivative come out 0, or the odd derivatives associated with the r degree x, they become 1 minus 1. So if I put this information together, here's the max series of sine of x. Okay, notice starts out with x, 1x. Why? Because that's the sine of x is approximate x around 0. That's why that 1x is there. And plugging 0, you get 0. Okay. So this is the max series in a closed in terms of written in terms of summation series. Okay, and this is a pictures of the progressively better and better approximations. Start out with a first degree, it's a red line. It's a red line over here, and then second degree is the, I guess the orange line somewhere over here. No, that's, where's the parabola in here? Oh, no, parabola, it's cubic. Right, that's third degree cubic, and there's a fifth degree, and et cetera, et cetera. Okay. Here's another algebraic expansions, and just show you the max expansions. And this actually comes out to be the formula we are quite familiar with. Take the first derivative, second derivative, third, you find out we have these patterns for the coefficients. Remember, we have to take each one of these divided by n factorials, okay? Which will just become 1. In other words, this is 1 plus x squared plus x cubed plus blah, blah, blah. And this is precisely geometric series formula. That's max expansions. Okay. And there's a basic summary of the formula for the expansions, and very basic. And then notice for log, we don't do it at x equals 0 because there's no expansion, x is not, log is not defined as 0. So we define these log 1 plus x, okay, functions. And it's a slight shift to the left. And here is the expansions of the log formulas. That's it. Okay, bye-bye. Okay. Well, I got a phone call. Never mind. Don't worry about it.